All right, today we're going to talk about t-test. T-test, let's start from examples. There are three different ways to do a t-test. One is t-test for single sample. And then we have a t-test for dependent means. And then we have a t-test for independent means. Let's start with a concrete example. I believe that single parents spend more time with their kids than parents on average. And census data shows that parents on average spend 2 hours each day with their children. I interviewed 6 single parents and found that on average, they spend 3 hours each day with their kids. Do single parents actually spend more time with the children than parents on average? Here's the data. These are the 6 people you interviewed. Jim, Mary, Joe, Kim, Kevin, Judy. These are 6 people. These 6 people are single parents. And you ask each of them, how many hours per day do you spend with your kids? Jim will say 4 hours. Mary, 2 hours. Joe, 3 hours. Kim, 3 hours. Kevin, 2 hours. And then Judy says 3 hours. These are the raw data. And you want to summarize the raw data. Summarize the raw data, we always get the mean and the standard deviation. You calculate the mean. On average, these 6 people spend 3 hours per day with their kids. And you look at what we know. We know that average parents spend 2 hours each day with their children. And your sample shows 3 hours. These 6 people are single parents. This sample on average spend 1 hour more than the population of average parents. Do you have enough evidence to show that single parents actually spend more time with their kids than the average parents? That's a question. Do you have enough evidence? Is the evidence from your sample strong enough for you to say, on average, single parents spend more time with their kids than the average parents? We can also calculate the variance or standard deviation. Remember, variance, you always get a sum of square deviations. Sum of square deviations, the mean is 3 hours. Some of the single parents are going to spend more time than 3 hours. First person, 4 hours, the 1 hour more than average. Second person, 1 hour less than average. Next 2 persons spend the same time as the average of the group. And then you get the deviation for each person. And then you square the deviation. Square deviation, you get the sum of squared deviation by adding them together. The sum of squared deviation is 4. The variance, sum of squared deviation divided by the degrees freedom, n minus 1. So the overall variance 0.8. And you know how to get the standard deviation. Standard deviation for the group is the square root of the variance. You take the square root of the variance. Now let's talk about the hypothesis. So we want to have a more specific statement of the hypothesis. Research hypothesis, a null hypothesis. Step one, we identify the population, the two populations. This hypothesis is concerned with two populations. Population one, single parents. Population two, average parents. These are the two populations you are concerned with. And then your research hypothesis, also called the alternative hypothesis, says single parents spend more time than the average parents with their kids. This you would be saying that on average, single parents spend more time than the average parents with their kids. The null hypothesis says, no, there's no difference. It doesn't matter. Single parents are just average parents in terms of how much time they spend with their kids. Single parents spend the same time as average parents. So the alternative hypothesis would be mu larger than, so mu for the mean, the population average for single parents would be larger than average parents. But for the null hypothesis, there's no difference. The mu, or the mean population mean for single parents will be equal to the mu for average parents. And then this is a null hypothesis versus Richard's hypothesis. The graph shows all the errors we can make. We can make a type 1 error, we can make a type 2 error. We can also make correct decisions. What would be the type 1 error? What would be a type 2 error in this case? Type 2 error. And that's for the review. Let's come back to this later. Let's come back to this later for review. We have our hypothesis, research hypothesis versus null hypothesis. And we want to show the null hypothesis is not good. We want to show that the null hypothesis should be rejected. How do we do that? First, we need to determine the characteristics of a comparison distribution. The distribution the sample square would have to come from, given the null hypothesis. So the comparison distribution. Let's see, in this case, we use a t distribution. The t distribution is very similar to the z distribution. The t distribution is similar to the normal distribution. And why do we use t distribution rather than the z distribution? This is because we don't know the variance or standard deviation of the population. You look at the question. So the consensus data shows that parents on average spends 2 hours each day with their children. We know that on average, average parents spends 2 hours with their children, but we don't know the standard deviation. We have no idea about the standard deviation of the average parents. We don't know. In this case, we use a t distribution. Suppose if we know that the average parents have a particular standard deviation or variance in terms of how much time they spend their children, we don't have to use a t distribution. We can use the z distribution directly. But usually, most of the time, we don't know the population variance or standard deviation. So we use a t distribution. And if we don't know the population variance or standard deviation, we need to estimate for that. we need to estimate that from the sample. In this case, we have a sample of 6 people. These 6 people, they offer a standard deviation. We can make an estimate of a standard deviation of the population from the sample. From the 6 people, we actually observe. So that is why we use T distribution. T distribution is a variant of Z distribution. It is very similar to the Z distribution. Let's look at the T distribution. Yeah, we can use a textbook, but there are so many good graphs on the internet. We might just want to search for one. T distribution. Yeah, let's look at a random T distribution. You see, the T distribution is very similar. It's very similar to the Z distribution. It's the same shape, and the T distribution just have more scores on the tails. The tails are larger for T distribution than the regular normal distribution. The normal distribution have more scores in the middle range and less scores in the tails than the T distribution. They are very similar, and there are ways to find the cutoff critical values on the T distribution. Let's see. How do you estimate the variance of the comparison distribution? In other words, we need to estimate the variance of the distribution of average parents. We know the mean. Mean is 2 hours. But what is a standard deviation? So we can start with the research data. Research data, this data according to the null hypothesis, the six people you have sampled in your sample are coming from the average parents. According to the null hypothesis, these 6 people are no different from the average parents. You can use these 6 people to estimate the standard deviation of the population of average parents. The key thing is that we are starting with a null hypothesis. Although these 6 people come from the population of single parents, but your null hypothesis says the 2 populations are the same. They are the same population. They don't differ from each other. Single parents and average parents, they are the same in how much time they spend with their kids. So this is really handy. This is really handy that you can use the 6 people in your sample to estimate the population parameter of the average parents. How do we do that? We can calculate the variance. And here, one more concept is the degrees freedom. Degrees freedom is n-1. n-1 is the degree of freedom. Is a degree of freedom. And the T distribution, the critical value on the T distribution is determined by the degrees of freedom. Let's look at the T distribution. See, Let's look at the t-distribution from the textbook. We already calculated the variance for the sample. The variance for the sample is a sum of square deviation divided by the degree of freedom. Sum of square deviation is 4, and degree of freedom is n minus 1. 6 minus 1, that's 5, 0.8. And based on this information, we can estimate the standard deviation for the distribution of means. Remember the difference between the variance of the population and variance of the distribution of means. We need to go from single scores to the means. And the relation is divided by the n number, divided by the number of people in the sample. In this case, the population variance 0.8 and sample size is 6. You divide by the sample size. So you get the estimated variance of the distribution of means. The M stands for distribution of means. From the variance, you can get the standard deviation. Take the square root of standard deviation. Let's look at a t-table. So here you have a t-table distribution. Let me open that and come back. You have so we have estimated the standard deviation of the population. This is estimated standard deviation to population of average parents. We know the average parents are spent on average 2 hours with their kids, with an estimated standard deviation of 0.365 hours. And now we need to determine the cutoff point. We are using the 5% level of significance. So we are using the 0.05. What does this mean? This means that we want to show that the difference between the sample average, that is 3 hours, and the population average, that is 2 hours, is unlikely to occur if there's no difference between the two populations. If there's no difference between average parents and single parents, and then the likelihood, the probability that we see this big difference, 2 hours versus 3 hours, is unlikely to occur, less than 5% probability. And then that means that the null hypothesis is no good. The null hypothesis is unlikely to be true. We reject the null hypothesis. So based on this p value, we can find out the cutoff point. The cutoff point for the t distribution is based on the p value, and also it's based on the degrees of freedom. You need 2 numbers to determine the t distribution cutoff. 2 numbers. One is a p value, 5%, and the other one is the degrees freedom, degrees freedom is n minus 1. And also, are you doing a one-tailed task or two-tailed task? That's also important. One-tailed or two-tailed. Let's get a t-distribution. So here's a t cut-off. The table would give you a one-tailed task, one-tailed task. If we are interested in, say, 5% probability, the 5% is located on one side. And if you want to do a two-tailed task, the 5% probability will be divided between the two tails. And then if you divide the 5% between the two tails, you would have 0.25. You would have sorry, here it's 0.25. Here you will have 2.5% on each side. Here we are doing a one-tailed task. Why do we do a one-tailed task in this case? Because we made a directional prediction. We predict that single parents would spend more time with the kids than average parents. We believe that the population mean of single parents will be larger than the average parents. That's why we are concerned with only one tail. We are making a directional prediction. And we're using the 0.05% level of significance. What is the degree of freedom? We look at the degree of freedom. Degree of freedom is 5. Here you have a degree of freedom 1, 2, 3, 4, 5. 5 is hard to tell, hard to see here. It's this row, this column 5. 2.015, 2.015. That is a t-score you need to get in order to reject the null hypothesis. You need a t-score that is larger than 2.015, or at least equal or larger than 2.015 to reject the null hypothesis. See here, this is a cutoff. And next step, you calculate the t-score, t-distribution. You see the t-distribution is very similar to the z-distribution. T-score is very similar to the z-score. You get the difference, the deviation here, the deviation from between your sample mean and the population mean. 3 hours, these 3 hours are based on the 6 people you measure, the 6 single parents. You got hold of 6 single parents, you measure on average, they spend 3 hours with their kids per day. And you know, the population of average parents spends only 2 hours with the kids per day. And you divide it by the standard deviation. This one is estimated. This is estimated standard deviation about the population of average parents. And this estimation is also based on the sample. This estimation is based on the sample of 6 people you measured. It's very similar to the same structure as the z-score. And your result is 2.74. 2.74. 2.74 is more extreme than the cutoff. You are looking for a score larger or equal to or larger than 2.015. Your calculated t-score is 2.74. That's larger, more extreme than the cutoff. And what do? You reject the null hypothesis. You would say that the result is statistically significant. We have sufficient evidence to reject the null hypothesis. We reject the null hypothesis, which says there's no difference between the single parents and average parents. And we support the research hypothesis, which says single parents actually spend more time with their kids than the average parents. That is a t-distribution, a t-test for single sample. The logic is the same as a normal distribution test, the z-test. You need to get the t-score, just like you get the z-score. And you need to get the cutoff, the probability, the proportion, the 5% cutoff. You can get it on one tail or on two tails. And you compare your calculated t-score against the cutoff. This is very similar to the z-test. Let's look at another example. In order to show that the workshop offered in an anti-alcoholism program has effectively reduced the number of beers students consume at each party, a researcher measured the number of beers consumed at a particular party by 6 students who have participated in the project workshops. You have the data. The data is based on 5 students. These 5 students, this sample, they have participated in the workshops. They attended the workshops. The researcher knows that beer consumption at a particular university is normally distributed. You know that at this school, students have a normal distribution on beer consumption with a mean of 4 beers. And the researcher does not know the standard deviation or variance of this population. That is a key point. We don't know the variance. We don't know the standard deviation, but we know the kids at this school had 4 beers per party. And that means that you need to use a t distribution rather than the z distribution. When you don't know the standard deviation or variance of the population, you do the t-test. You use a t distribution. When you do know the standard deviation or variance, you use a z-score. You use a normal distribution, simple. You don't have to convert it into a t distribution. Can we reject the null hypothesis at 0.5 level? So that is the key question. That is the question we are asking. Does the workshop work? Does the workshop really make students consume less alcohol? Do we have enough evidence to show that? Where is the evidence? Show me the evidence. Here are the evidence. We ask 5 people: Jim, Mary, Joe, Kim, Kevin. These 5 people, they attended the workshops. Are they drinking less? Are they drinking less than the population? Jim had 1 beer. Mary had 2 beers. Joe 3 beers. Well, you see that all of them had less beers than the average person. The average was 4. The mean of the population was 4. But these people have only, all of them have fewer than 4. and we can calculate the mean. The mean and the standard deviation, the variance. These are the descriptive statistics. Descriptive means we are calculating statistics based on the sample, based on the people we actually observe. And you follow the regular routine. The mean is 1.6. That's way lower than the mean of 4. On average, people drink 4 beers at the university. But the average of these 5 people is only 1.6. And then what is the standard deviation? What is variance standard deviation? The variance, you get the sum of squares for the variance. Sum of squares, sum of square deviations. The deviation. Gene is below the mean. 0.6 beers below the mean. Mary is above the mean. And Joe is above the mean by 1.4. You get the deviations, you square the deviations, add them all up. The squared deviation, 3.2. And then you can calculate the variance of the 5 people. These 5 people, they have a variance of 0.8. Sum of square deviations divided by n minus 1. That is a degrees freedom. So this one is based on the individual scores in the sample variance. But you're not interested in the sample variance. Your real interest is the variance for the distribution of means. The variance for the distribution of means of samples with 5 people. According to the null hypothesis, these 5 people are coming from the general population, the population of average college students. And you want to estimate the distribution of all the means, all the possible means of samples with a sample size of 5 people. In this case, you take the population variance and divide it by the n number, divided by the number of people in the sample. That's 5. So here you have the estimated population variance. And then you take the square root of the variance, you get the standard deviation. Yeah, these are the simple statistics that you need to take care of before you do anything else. Let's look here. The research hypothesis, we also call it alternative hypothesis. What is alternative hypothesis? Those students who participate in the workshop, this population drink less on average than the average students. That's the alternative hypothesis or research hypothesis. This is when we are trying to support. We are trying to show that the participants to the workshop, anti-alcoholism workshop, actually drink less on average than the average students on campus. But we start with the null hypothesis. The null hypothesis basically says the workshops have no effect. The workshops have a zero impact on drinking behavior. Participants in the workshop, they drink the same amount on average than the average college student. That is what we are concerned about in the null hypothesis. We try to use evidence, we try to use the data, To embarrass the null hypothesis, we try to use the data to show the null hypothesis is not likely, it's unlikely. If the null hypothesis is true, suppose we start from the assumption that the null hypothesis is true, the two populations do not differ from each other in how much they drink. And then the difference between 1.6, the average of these 5 students, and the population average 4 is unlikely. Unlikely. How unlikely? Less than 5%. Less than 5%. And we use the t-distribution to show that the t-distribution is highly similar to the z-distribution. And you can divide the proportions, the different proportions. The more extreme scores on the t-distribution, the less likely they occur. Extreme scores, extremely high or low scores, have a small probability on the t-distribution, just like the z-distribution. And we want to show, in other words, we want to have a extremely large or small t-score. We want the t-scores to be extreme, either extremely large or extremely small, to have a small probability. That's what we want to show. And how do we do that? So let's see here. Research hypothesis, and then so we need to determine the cutoff. Let's see, the p-value is 0.05. We want to use a 0.05 level of significance. Let me write it down here. P-value is smaller or equals to 0.05. That's one piece of information. Do we want to do a one-tailed task or two-tailed task? Do we want to do a one-tailed task or two-tailed task? In this case, we want to do a one-tailed task. Why? Because we made a directional prediction. We predicted those people who go to the workshop will drink less. That is directional. The people who go to the workshop will drink less than the general student population. One-tailed task. And what is the degree of freedom? n-1. In the sample, we had 5 people. So 5 minus 1, that's 4 people. Degree of freedom of 4. Once we get this information, we know the cutoff t-value. So the cutoff would be look at the t-table, degree of freedom 4 and one-tailed significance level. Let's see, 0.05. 0.05 degree of freedom is 2.132. 2.132. 2.132. And in this case, do we want a negative cutoff or positive cutoff? Probably we want the negative. we predict that the population of students who go to the workshop will drink less than the average students. So we're predicting that the mean of workshop participants minus the mean of the average population would be negative. So we have a negative cutoff. And next we calculate the t distribution, t-score. T-score, let me copy the formula. T distribution, t-score, the sample mean, this 5 people we measured, on average, how many beers will they have? 1.6. And the population of college students have mean of four beers. I remember the standard deviation we estimated. Here's the estimated standard deviation. 0.4. And this is a t-score. Let me go look at that. 1.6 minus 4 divided by 0.4. 6, negative 6. The t-score is negative 6. Is that more extreme than the cutoff? Yeah. Oh, I got wrong place. Yeah. So I pasted this one in the wrong place. Here. T distribution. Yeah, this is the right place. This is the correct place. Okay, yeah, you find the cutoff. And you get the t distribution, the t-score. No, that's not. Where did it go? Let me do it again. So t-score is 1.6 beers minus 4 beers, and the standard deviation we calculated was 0.4. Oh, I know where. So that's the wrong place. We're looking at the example 2. Oh, okay, here it is. Here it is. Yeah. On average, these 5 people had 1.6 beers. That's way less than the 4 beers on average. And then the standard deviation you estimated is 0.4, and the t-score is 6. T-score is 6, and that's more extreme than the cutoff. Yeah, more extreme than the cutoff. So we do reject the null hypothesis. We say we have sufficient evidence, we have enough evidence to show that the workshops work, The workshops effectively reduce the number of beers students drink. That was a t-test for one sample t-test. Now let's look at a t-test for dependent means. T-test for dependent means also come from one sample, but this one sample gave you two scores. Look at this example. A researcher wants to test the effectiveness of a new therapy for snake phobia. Snake phobia is a fear of snakes. Some people are really afraid of snakes. He believed that this therapy would reduce people's fear of snakes. He recruited 6 people with snake phobia. These 6 people were all afraid of snakes. Before giving the treatment, he measured each subject's fear on a 0 to 10 scale. This is called a pre-test. Before the therapy, you test their fear level. From 0 to 10. 0 means not afraid at all. 10 means extremely afraid. The higher the number, the higher the fear. And then he gave each person treatment. He treated each person. Help them, maybe this is behavior therapy. You make them interact with a harmless snake so they get used to it. They are no longer afraid of it, hopefully. And after the treatment, immediately after treatment, he measured the subject fear of snakes again using the same scale. You have the data. What I'm trying to show is that the treatment works. The treatment reduces people's fear of snakes. Here's your data. You have 1, 2, 3, 4, 5, 6 subjects. Before the therapy, you measure their fear. For this guy may be Joe. Before getting therapy, his fear level was pretty high. 9 is really fearful. And you give them treatment. After the therapy, he gets much better. His fear level is 2, so that's an increase. That's a big improvement. Big reduction in fear. Subject number 2 also made a lot of progress. Before the treatment, fear level was 10. After the treatment, dropped to 3. And you see the pattern. All people made improvements, reduce fear. Do we have enough evidence? Do we have enough evidence to show that the treatment works? Looks like that. It looks very promising. But we need to do the appropriate statistical test. We need to show it statistically that result is significant. Are these results significant? That is a question. First of all, we summarize the data. How do we use the data? We are interested in the difference. We are interested in the difference score. The difference between the pre-test and post-test. Here, for subject number 1, the improvement or the difference is 7. For subject number 2, 10 minus 3, improvement is 7. Number 3, improvement is 7. And number 4, subject number 4, he made a smaller improvement, improving from 8 to 3, that's 5. And you calculate the difference. Everybody showed a positive difference. And you show the average difference. On average, how much people improve from before the therapy to after the therapy. The average improvement is 6.67. That's pretty large. 6.67 is average improvement. The difference from pre-test to post-test, this is a statistic we are using. We are using this statistic to show the therapy works. So we focus on this statistic. We get the mean improvement and we get the standard deviation. Standard deviation on the improvement or the difference. And each person has a deviation. Subject number 1 improved more than average. The first 3 subjects improved more than average. And then the next 2 improved less than average. The last person improved way more than average, improved a lot. And then you have the square deviation, you get sum of square deviation. Sum of square deviation are the difference scores. And then you can get the variance. The variance stands as sum of square deviations divided by the degrees freedom, n minus 1. And you can get the standard deviation on the difference scores. This is basic statistics. It's always good habit to get the basic statistics. Get it out of the way. Get it ready. Well, we need to state the research hypothesis and null hypothesis. So here, we need to state the 2 populations we are comparing. Population 1, what are the 2 populations we are comparing? Population 1, snake phobia patients before population 1 would be snake phobia patients before receiving therapy. And population 2 would be snake phobia patients after. It's before and after. These are the 2 populations we are interested in. Hypothesis. What would be the research hypothesis? The research hypothesis would be higher level fear you're saying that people with snake phobia before receiving therapy would have a higher level of fear than people with snake phobia after receiving therapy. That is a research hypothesis. The null hypothesis would say the 2 populations do not differ. Yeah, so that's two hypotheses. You are trying to reject the null hypothesis and support research hypothesis. Yeah, I need to go to the bathroom. Let me go to the restroom. I'll be right back. All right, let's see. So these are the two hypotheses, research hypothesis versus null hypothesis. Research hypothesis is also called alternative hypothesis. So we can write it as H sub A. Null hypothesis is H sub 0. And then you want to determine the comparison distribution. Comparison distribution gave you the probability, give you the proportion. The proportions would give you the probability distribution. And what is a comparison distribution we are using? We are estimating population variance. We don't know. We have no idea of the variance in the population. And so we use a t distribution. And the mean of the comparison distribution is going to be 0. Why? Why is it 0? Because we are using a difference score. This is called a pre-task, post-task difference. Suppose if the null hypothesis is true, suppose if the two populations have no difference, before and after, pre-test and post-test, before receiving therapy versus after receiving therapy, no difference. And then on average, the difference score would be 0. The difference between the pre-test and post-test would be 0, according to the null hypothesis. But in this sample, in our sample 6 people, it's not 0. The difference is pretty large. This is pretty far away from 0, 6.67. And that's different from 0 by a long shot. Do I have enough evidence to say that the mean difference in the population is not 0? That is what we're trying to show. So we need to use a comparison distribution with a mean of 0. This is a difference score. Difference between pre-test and post-test is 0. We know the mean. The mean is 0, but we don't know the standard deviation. We don't know the variance either. We need to determine we need to estimate from the sample. And from our sample, the variance we estimated from the sample is this one. So here, SS, sum of square deviation, we got the sum of squared deviation. This is based on the difference score. All the differences squared, we add them up. We got 5.34. And we divide it by n minus 1. We get 1.068. Now we need to divide it by n. We need to divide it by the sample size. Sample size is 6. Now we have a distribution of means, sample means. This is the estimated variance of the different distribution of sample means with sample size equals to 6. Take the square root, we get the variance. We get the estimated variance for the standard, for the distribution of means, 0.46. Once you get the standard deviation, you're ready to get the t-score. Standard deviation, the mean, and the raw score, you got enough information to get the t-score. So your comparison distribution is a t distribution. It is a t curve. And the degrees freedom is 5. Degree freedom is 5. The mean is 0. Standard deviations 0.43. Cutoff. We're doing a one-tail test. Why? Because we make a directional prediction. We are predicting the pre-test fear is going to be larger than post-test fear. People are more fearful before the treatment than after the treatment. One-tailed. Now we need to find the cutoff. Let's see, 0.05. One-tailed, degree freedom 5. It's 2015. Yeah, here's a t-square cutoff. You want your t-value to be more extreme, to be larger than 2.05. Now we are ready to get the t-score, get the t-value. Your sample difference, on average, your difference score in the sample, we calculated 6.67. That's how much improvement people made on average between this among these 6 people. And you subtract 0. What is 0? 0 is coming from the null hypothesis. According to the null hypothesis, on average, the difference between the pre-task and post-task it should be 0, no difference. And you divide by the standard deviation. Standard deviation, oh, I got a typo here, so it should be divided by 0.43 rather than 0.42. Let me do that again. 6.67 divided by 0.43. 15.51. Still really large. That is your t-value. Is that more extreme than the cutoff? It is by far more extreme than the cutoff. So, what's your decision? We decide to reject the null hypothesis. We decide to reject the hypothesis that there's no difference between people's fear before receiving treatments and after receiving treatment. And we support the hypothesis that people's fear after treatment would be significantly lower than before the treatment. We support the reset hypothesis. We have sufficient evidence to show the therapy works. The therapy effectively reduces people's fearfulness of harmless snakes. This is one example, pre-task, post-task design, t-task for dependent means. Let's look at another example. A researcher believes that testosterone is a male hormone. Male hormone increases aggressiveness in male animals. He got 3 male rats as his subjects, and gave them a large dosage of testosterone, gave them a shot, increase their testosterone level. And he measured the number of times each rat attacked other rats before and after the injection. Each rat would give you 2 numbers, aggression before injection and after injection. Now we want a different p-value. Significant level smaller 0.01. That is more stringent than 0.05. And let's see. Let's calculate the basic statistics. 3 rats, 3 subjects. Number 1, before the injection, you test he attacked other rats 2 times. 2 times maybe per 2 times per hour or per 30 minutes. And then after injection, he got aggressive. He got more aggressive. He attacked other rat 9 times. And then the second rat, number 2, before the injection, he was kind of mild. He attacked other rats 2 times. After the injection, he got more aggressive, 6 times. The last one, before injection, 5 times. After injection, 9 times. All rats just showed an increase in attack. And then you calculate the difference. The first one got an increase of 7. Second, increased by 4. Last one, increased by 4. The difference differs. The first one really got a boost. First rat got a big boost. The number 3 and number 2 and number 3 to a lesser degree. You calculate the average. On average, what's the difference? 5, increased by 5. And you get the standard deviation and variance of a difference. On average, the rats got an increase by 5. And you get the deviation score on the difference and squared deviation. Sum of square deviation on the difference score, 6. And then you get the variance, SS divided by n minus 1. So that is the basic statistics. And you get the t-score. Get the t-score. How would you calculate the t-score? You need the distribution of means. Distribution means here, you need to divide it by the number of people in the sample. You know the variance for the population. The variance for the population is 3. These are based on individual scores. N equals to 1. And you need to divide it by 3, the n number. So the standard deviation and the variance are both 1. 5, and then you take the t-score. You get the t-score, t-value, -5. -5, you compare the -5 against the comparison distribution. You compare it against the cutoff. Let's get a cutoff. Cutoff for t. Where p value is smaller or equals to 0.01, is one-tailed, two-tailed, one-tailed. Is one-tailed, and the degree freedom is 2. That'll be sufficient for you to get the cutoff. Look at the t-table. Now we have a different p-value. P-value 0.01. We're doing one-tailed test. We're doing one-tailed. So we look at p 0.01. Degree freedom 2. Here, right here. So the cutoff is 6.965. Which is right here. .165. Let me check that. 2-degree freedom, 6.965. It's going to be negative. We are concerned with the negative side. This will be the t-value you will need to reject the null hypothesis. In this case, your calculated t-value is -5. Would that be sufficient to reject the null hypothesis? No, not extreme enough. -5 is not enough. You need a t-value that is more extreme than -6.965. In this case, we don't have sufficient evidence to show that testosterone injections increase aggression. We don't have enough evidence to support that. In other words, our result is not sufficient, not significant at the 0.01 level. Would it be significant on the 0.05 level? Yeah, it would be. All right, so that's a t-test for dependent means. Now let's look at the t-test for independent means. Example 1, researchers interested in the effects of people's experience on their fearfulness when they do scary activities like a parachuting, bungee jumping. Those are very scary activities. He thought that experienced people would be less fearful than novice, inexperienced people when they engage in scary activities. He did an experiment. He had 6 people who are going to undertake their first parachute jumping activity. The first timers, never done it before. Like me, I've never tried parachuting. And he also got 6 people who have trained in the parachuting club for more than a year. These are experienced. These people have been doing it for more than a year. And the researcher measured each subject's fearfulness just before they jump from the plane. And he used a scale of 1 to 10. 1 means not fearful at all. Really no fear, it's okay. And then 10 means extremely fearful, really fearful, scared, freaking out. Here you have the data. Altogether, you have 12 subjects. You number them from 1 to 12. Here, you can code the experience. 0 means no experience, new to the game. 1 is experienced, trained more than 1 year, more than 1 year of training received. And then the dependent variable is fearfulness, how fearful they are. This group is really fearful. the first timers were really fearful. On the other hand, those people who are experienced or less fearful. You are comparing these two groups, two independent groups, independent samples. Sample one are not the same people as sample two. These are different people, different from the pre-test, post-test. How do you state your research hypothesis and null hypothesis? You are concerned with two populations. One population, first-timers, no experience. People who have no experience in parachuting. Population two are those people who have more than 1 year's experience in parachuting, experienced parachuters. You are comparing these two populations. Your research hypothesis, mean fearfulness of first-timers will be higher than experienced parachuters. Between these two populations, population one will have a higher fearfulness on average. And then the null hypothesis says there's no difference between the two populations in fearfulness. The mean of population one would be equal to the mean of population two. These are the hypotheses. You are trying to use your evidence to reject the null hypothesis. You are trying to show that the null hypothesis is not good. Given the null hypothesis, it's unlikely for you to have this kind of data. And then step two, the comparison distribution. What is a comparison distribution you are using? This is one that gave you the proportion. The proportion, the probability. And in this case, you are using the t-distribution. And suppose if the null hypothesis is 2, the difference between the two populations would be 0. Two populations would not be having any differences in fearfulness. They have a 0 difference according to the null hypothesis. And we're using the difference between two samples, two sample means. We can get the mean of the experienced people and the mean of the inexperienced people and calculate the difference. Is the difference equal to 0 or is it far from 0? That's what we are looking for. Let's calculate the means, or the mean between the two, the mean of the two groups. The mean for the first-timers, inexperienced group. On average, their fearfulness level is pretty high, 9.17. 9.17, that's a high fearfulness. And we can get the sum of square deviations, SS for group 1, SS for group 1, 2.84. And you can calculate the variance. The variance for based on group 1, SS divided by n minus 1. How about the other group? The experience group, you get the mean. Well, the mean is way lower. Oh, the mean is way lower than the first group. And you can get the deviation, square deviation, sum of square deviation. Then you get the variance. The variance from group 2. And you take a difference. The first group is way more fearful than the second group. 9.1 is the difference between 9.17 and 2.50. The difference is pretty big, 6.67. According to the null hypothesis, the difference between the two means should be 0. That's a null hypothesis. But your evidence is showing that no, it's not really a 0. It's your sample, the two samples you measured is far from 0. They're pretty different. Now you need to calculate the t-score, t-score. The key feature of the t-score is a standard deviation. Standard deviation is a key thing. In this case, you need to take several steps in calculating the standard deviation. So here, first, you want to prove the standard deviation. You want to prove the variance. You have two estimates. You have two estimates of the population variance. One is based on sample 1. This is an inexperienced group. Another one is based on sample 2. Two estimates. You want to pool them into one single estimate. And let's see. From sample 1, you have a weight. So the weight is based on the degree of freedom, total degree of freedom. What is the total degree of freedom? Let's look at the sample 1. Sample 1, you have 6 people. 6 people minus 1, that's 5. 5 degree of freedom. How about sample 2? Sample 2, you also got 6 people, and degree of freedom is also 5. And the total degree of freedom is a sum of the two groups, 10. 5 plus 5, that's 10. And the weight for the pooled variance in each term is the proportion of degree of freedom. For sample 1, it's 5/10. For sample 2, it's also 5/10. This is because the two groups have equal numbers. Both groups have 5 people. There could be an unequal n situations. In some situations, one group has more people than the other group, and then the weight of the two estimates would be different. In this case, basically you get a weighted average of the two estimates. In this case, the two estimates have equal weights. The pooled estimate would be 0.48. Now, this is not what we're going to use for calculating the t-score. But this pooled estimate is the variance of distribution of single squares. We got these estimates based on single squares, 1, 2, 3, 4, 5, 6. This is not what we're going to use. It doesn't match the data we're using. Our data is the difference between sample means. We want to get the difference between two samples, experienced, inexperienced. And now we need to estimate the distribution of the differences between two means. Differences between two means. According to the Null Hypothesis, the two populations are from the same distribution. The two populations have the same distribution. Inexperienced and experienced people do not differ. And we have estimated the variance of this distribution. That is a pooled estimate based on the two samples. Now we need to estimate the distribution of means. Distribution of means. And this estimate depends on the sample size. The larger the sample size, the smaller the variance and standard deviation. And we need to divide the population variance by the sample size. Here, suppose if the two sample sizes differ, we would have a different denominators. But in this case, we have the same sample size. For both samples, we have 6 people in the sample. We just take the pooled variance divided by sample size together. And when we are estimating the distribution of differences, we need to add them up in estimating the variance. This will be the difference between the M1 and M2. This would be the estimated variance of the difference between two samples. Sample of experienced subjects versus inexperienced subjects. In this case, you add them up. And then you get the standard deviation. You take the square root, Now you have the estimated standard deviation. Almost ready to get the t-score. And now we determine the cutoff. Cutoff, we are doing a one-tailed test. Why? Because we are making a directional prediction. We are predicting one group is going to be more fearful than the other group. And we are using the degrees freedom. We are using the degrees, we are using the p smaller than 0.01 level of significance. And we need to find out the cutoff. To find the cutoff, we use a DF. DF here, what is the DF? Total DF. That would be 10. The sum between the two groups. In this case, let's find the DF. let's find the cutoff. df equals to 10 here. Here 0.01, 0.01, 10 df 2.764. Uh, 2.764. So we need a value, t-value more extreme than this one. Now we are ready to get the t-score. T-score, the difference between two sample means, we got that. The inexperienced group mean 9.17. Experienced group mean 2.5. And the standard deviation 0.53. This is t-value you calculate. The t-value is pretty big, it's really large. Way larger than the cutoff, more extreme than the cutoff. In this case, do we reject the null hypothesis? What is the decision? Yeah, we reject the null hypothesis. We have sufficient evidence to reject the hypothesis that says there's no difference between the two populations. And we support the hypothesis that the inexperienced parachuters would have more fear, higher level fearfulness than experienced parachuters. All right. This is an independent means. T task for independent means. Two groups are really different from each other. Look at this one. Look at another example. We don't need this one. Researchers believe that single mothers spend more time with the children than married mothers. Here got a hold of 6 single mothers and measured how many hours they spend with their kids. And he got hold of 6 married mothers and measured how many hours they spend during the same period of time. You have the data. Now you want to do a hypothesis testing. Now you have 2 groups. One group, single mothers. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, right? So it should be 7. So actually I got the number wrong. 7 single mothers and 7 married mothers. N number is a 7. Second group, N number is 7. You get the mean. On average, the single mothers spend 6 hours in this group. Married mothers, 3 hours. And you can get the deviation. Deviation For this person, 0, -2, you get some square deviations. Some square deviation for two groups. And you get the degree of freedom. Degree of freedom for the first group, 6. Second group, 6. And let's get the t-score. For getting the t-score, we need several steps. First, we have 2 samples. Each sample would give you a variance. Each sample would give you an estimated variance of the population. We need to pull them together. And that's a weighted average of the 2 estimates. Weight, where's the weight? The weight is the proportion of the degrees freedom. In this case, we have an equal n number between the 2 groups. So the 2 weights will be the same. Each one is half, 0.5. And the first group gave us an estimate of variance 4. That's the estimated variance. From group 2, we got an estimate of 4.33. We get the weighted average of these 2 estimates. Overall, the pooled estimate of the variance, 4.17. 4.17. Remember, this one is based on individual scores, But we are interested in the mean, the distribution of means. And how do we do that? Let's carry out the rest of the procedures. We got the pooled estimate, and now we need to get the distribution of means. A distribution means the variance. For the first group, for both groups, we use a pooled estimate. So we use a pooled estimate. For the pooled estimate, is the same, 4.17. And we divide it by the n number. In this case, the n number is the same in 2 groups. They're both the same. So we're going to get identical estimates. 4.17 over 7. 4.17 divided by 7. No. 4.17 divided by 7. Yeah, 0.595, 0.596. 0.596. For this guy, the same thing. Yeah. We're doing the procedure twice, just in case the 2 groups have a different n numbers. If 2 groups have a different n numbers, they will have the different weights. And we got 2 estimates of the distribution means, but we are interested in the difference between two means. Mean 1 minus mean 2. We're not interested in it. So we're interested in the difference between two means. Difference between two means. That means we need to estimate the variance of the difference. The variance of the difference between the two means. We need to add them. Yeah, so this case will be easy. Times by 2. 1.19. 1.191. Now, are we ready to get the t-score? Yeah, we're ready to get the t-score. The difference between the two means, where are the difference between the two means? Mean 1 is 6. Mean 2 is 3. Six minus 3. So what is the standard deviation? Standard deviation 1.191. 3 divided by 1.191. 2.519 is 2.519. That is a t-value we get. So we got the t-value. The result is based on the t-value. Now, you need to compare the t-value against the cutoff. So did we get the cutoff? No, so we need to get the cutoff. Cutoff t-value, how do we go get that? We need t-value. Do I have the p-value specified? Yeah, suppose we use t smaller or equal or smaller than 0.05. We need the p-value to get the cutoff. P is smaller or equal to 0.05. We know that. But now we need to know the degree freedom. df. Degree freedom will be the total. For group 1, 6. For group 2, also 6. 7 minus 1. So 12 is a total degree freedom. Are we going to do a one-tailed test or two-tailed test? In this case, it's one-tailed. We are predicting mean 1 will be larger than mean 2. Mean 1, so the fear the inexperienced group will have more fear than the experienced group. So we do a one-tailed test. Look at the cutoff. 0.05, 12, 1782. T 1.782. That is a cutoff. In other words, you are looking for a t-value larger than 1.782 to reject the null hypothesis. And you compare your t-value with the cutoff. Your t-value is 2.519. That is more extreme than the cutoff. Yeah, in this case, you reject the null hypothesis. Now, here's your decision. We decide to, based on this result, based on the t-value 2.519, we decide to reject the null hypothesis, which says the inexperienced population would have the same level of fearfulness than as the experienced population. And we do this because if the null hypothesis is true, there is a less than 5% probability that we would observe a t-value this large. The probability that we get a t-value larger or equal to 1.78 is equal to or less than 5%. Our result is significant at a 0.05 level. This is why we reject the null hypothesis. In other words, we support the research hypothesis or the alternative hypothesis. We have sufficient evidence to show that the two populations, the experienced versus inexperienced populations, have a different level of fearfulness. To be more specific, the inexperienced parachuters have on average more fear or higher levels of fear than the experienced population of parachuters. Yeah, so those are the 3 types of t-tests. This part is very important, always get tested. Yeah, so go through these examples really closely. I'm going to send you guys the link. I'm going to send you guys to the link of the video probably today. And also, in the textbook, they have some really good quizzes, good practice. Quiz 26. That's really good. So you guys should do a quiz 26. Let's look at quiz 26. Yeah, you are ready to do all these questions. All right, time is up. Time is almost up, guys. Let's call it a day today. I will send you guys the link. Watch for your email.